Okay. The week before the holiday, I have discussed with you, or the after the holiday, we have the discuss the regression modeling. So I have mentioned this one is the linear models, what we have considered. Okay. So in the linear models, of course, they consist of the errors terms here. So these error terms, they have assumed for the certain distribution. Okay, so we have this one is a linear models where I call it as a first order model here. Okay, and the first order model, you plus the iteration term here, then you can have another type of the models here where you have a x1, x2 and a x1, x2. So this one was related to the design of experimenter. What we have studied before, you consider the factor A, factor B, and the factors AB. So this one is all related to the design of experimenter later on where we want to write down the equations. Okay, so you have a factor, iteration factor of the AB. Okay, then also you can have another one is called the second order model. So the second order model will include the quadratic terms inside here. Okay, so you have x1, x2, x1 square, x2 square, and then the iteration effect. Or the x1 square in the model, however, the x2 square will not in the model. But this one is considered as a full model you have. Okay, so all these models, we can transform it to the linear models where the variable of the x1 and the x1, x2, x1 square, we can denote it as a x3, x4, x5. So this one is an end out. We still have a linear models. Okay. So I have discussed you how do you in the linear regression model, how are you going to estimate the parameter? Okay, because you want to find the fitted equation, therefore you need to find what is your the estimated parameter here is a beta 1 hat and beta naught hat. So this one is for the case of the simple linear regression. And then you also go through is what you have is a multiple linear regression where you have a beta naught until the, after that you have beta 1 until the beta k. Okay, if you have a k factors, then you need to have a beta naught until the beta k. Okay, if you consist of the full models. So how to estimate it, I also have shown it to you using the least square technique or the maximum likelihood techniques where they try to estimate. This one is the beta hat where how you estimate the parameter. Okay, so after that we can test the significance of the models, and then we also can test the significance of the each of the beta here. Okay, so this one is what I have discussed you all in the previous case. Okay, so following by the regression analysis, okay, you can go through it this thing. Okay, we will go through the following chapter. This one is called the response surface methodology. Okay, so this one, the response surface methodology, will related to the regression model. Okay, so the regression model is just extra, or where I let those of the students who are not familiar with what is a linear regression model. This one is how to do it, and then how do you estimate parameter. And then because later on my example also involve the x prime x inverse, how do you calculate the beta hat will be given by the following one. Okay. So now we will start with the following chapter. It's called the response surface methodology. So under this response surface methodology, we want to include those of the factors in the model. Okay, so in our study before, we have a factors, we have a different factors, factor A, factor B, factor C, and so on. We have many factors, as well as if you study the factorial analysis, then you have iteration effects. So now you also can include the quadratic component in the model itself. Okay, so factors are processing condition or the input variable whose the value or the setting can be controlled by the experimenter. Okay, so this one is what you have studied before. So the factor and the variable were denoted as x1 until the sk respectively. Okay, so you have a x1, is a factor 1, x2 is a factor 2, xk is a factor k. But for the x1, you have a different level. So therefore, they consist of the, if you study is the 2 levels, then they consist of the value for the 2 levels. If you study the 2 power k factorial design, then they have a -1 and the +1. Okay, so this one is what we have here, because we want to identify the important factors and then put in the equation. So the response variable is your y. Means that before that you also observe that your y is your response variable, or your observation you have is measure quantity whose the value is assumed to be affected by the changing of the level of the factor. Means that before that you identify which is important factors. Okay, you identify the important factor. Then from the important factor, then you can form the equation. Okay. So the true response, if we call as a eta, is depends on the level x1 and the xk of the k quantitative factors. So we have a response of the here. Later on the following page, I will show you the response surface. So the function is called the response, the true response function. So we have a following function, and then we want to see what is the function is look like. Okay. But of course, I do not expect you to draw it out the function. Okay, so I give you the, for example, if k is equal to 2, we only study the 2 factor. The first factor we consider is a pressure. The second factor is a temperature. So we have a x1 and x2 will affect the process yield. So the process yield will be the response. So we denote it as a y. Then the x1 and x2 is the pressure and the temperature. So we can have the different level. For the x1, they can take the value maybe the 1 and the 2. Okay, you have a pressure 1 and the pressure 2. You denote it as a 1 and 2. For the temperature, you also can have let's say the 40 degrees Celsius and the 60 degrees Celsius and so on. You depends on how many levels you have. Okay, so this is x is your response variable. Sorry, not the response variable. Is your here we call as the input variable here. Or some of you study the regression, linear regression before. All these things is called the independent variables. Okay, so our model we can write in the following one: y is equal to the response plus the error here. Okay. So the model is given by here. If you're going to fit the linear model here, then this one, the first order model, then we have a following linear models. It's a beta naught until the beta k xk. So in this example, the k is equal to 2. Therefore, you only have a beta naught, beta 1, and beta 2. Provided that these two factors are significant different. If these two factors, they do not have any contribution to estimate for your y, so therefore your model maybe only consists of x1 or x2 or both together. Okay, so since you study for the 2 factors here, then we also can go to the second order model. So the second order full model, what I say full model is means that I include all the terms here. But sometimes certain terms is not significant, we will drop the terms here. So similarly for the second order model, okay, for the second order model, we consist of beta naught for the beta I, xi, and then we also can have a quadratic term here, and then the iteration terms here. So if we consider a full model, then we list down all the possible cases you have. Okay. So this one is called the model we're going to do it. So this one is similar to what I have discussed with you, regression modeling parts. Okay. So what is the contour look like for the response surface? Okay. So a technique used to visualize the shape of the 3-dimensional response surface is plot the contour of the response surface. So what is the response surface look like? With this one is what they look like here. So this one is the temperature and the pressure here. Okay, we draw in the 2-dimensional one. The temperature, they consist of 100 until 160. The pressure is from 10 until the 40. Then the y is here the mean of the response. So this one is what is a graph for the here. So as you can observe it, this one is one of the response surface of here. Okay. So from the response surface here, we have a control plot here. So how the control plot look like? You draw the you just slide it for each one of them. Okay, you just use a knife to slide for each one of the layer. Then you can see that they look like the following form. You slide the first one, and then you get the circle. You slide the second one, you get another circle. Okay, so this one is called the contour plot of here. Okay. And then for the rest, the following one, the third one of here is talking about we have why we need to have a response surface here, because why we need the equation of the model, because from the model itself, if we can fit our factors and the response, we kind of can find the relationship of these two, then we can find out the models. Then based on the model here, we can find the fitted value or the predicted value of the y here. Okay, so under the response surface idea is the first thing you have the response surface given by the following one, or in terms of the quantum. So if you observe it here, our experiment we run is under this stage. Okay, it's under this stage. So we want to get, sometimes we want to get the maximum problem, or sometimes we want to look for the minimum problem. So we want to have a maximize the yield or minimize the risk. So therefore, we need to find out what is the equation lead us to the maximum or to the optimal solution. They can be the maximum, can be the minimum. So this one is how the graph is look like. Under the response surface methodology, we start the process is running here. Then after that, we run the process, follow the certain path. Okay, the path is called the path of improvement. Then we go towards the optimal solution, where the region is for the optimal solution. So in detail about this thing, I will discuss you in the second part of the response surface methodology. Okay, so from the first one, from here and then towards the direction. Okay. So you can observe that this one is the graph of the response surface. This one is a control plot. Okay. Of course, we are not going to draw it manually. Okay, for this type of the plot, but at least you know that there is a such plot where you can be draw it out. Okay. So now we will go through the regression analysis. Okay, the regression modeling part, where we have an equation of the regression model. Okay, where I mentioned it here before. Okay, you have a following one example. Maybe I show you is this one. You have this one is some sort of like the 2 power of k, 2 power of 3 factorial design. Then you list down all the possible treatment combination, and then this one is your response of the y. Then to find the fitted equation, then you find out the beta hat. Find out the beta hat using the following formula, then you can get your fitted equation. So if you want to fit your equation with only the main factor, therefore you have a x1, x2, and x3. If you want to fit the equation with all the iteration as well, with the 3 factors, then your equation also involve the iteration effect. So means that you have x1, x2, x3, and so on. Okay. So in the following analysis here, okay, we will go back to the what we have studied before is a 2 power of 3, 2 power of k, 2 power of k factorial design. Okay, so we will concentrate on the 2 power of k factorial design. How under the 2 power of k factorial design, I have teach you how to go through the effect, how to calculate the effect, how to calculate the sum of square. So these two I have mentioned it to you by using the contrast. Okay, using the contrast, then you can cut the effects and the sum of square. So now we want to form out the equation. Okay. So I will put it here. This one is an example from the previously what you have here. The low level, the high level at the factor A, the high level at the factor B, both of them at the high level here. Okay, so these are the notation you defined before, 1, A, B, and the AB. Okay, so these are the notation or they given by here. Okay. So based on this example, what we have discussed before, okay, my concern is only for the regression model, but because I introduced this example, I need to provide for you the rest of the information. Okay, so in this particular design, we have calculated out what is the effect. Okay, effect is 1 divided by n times 2 power k minus 1. So therefore, you calculate the effects is using the contrast. You calculate the effect is here. Okay, so the effects for the factor for the following one is calculated by using here, and the effect for the B and the effect for AB. Okay, these are the 3 effects you calculate from the following example. Okay, so how to calculate effect? I think that you can refer back the 2 power k factorial design. Okay, so now we will relate it to the regression model. So under the regression model, if we want to do this thing, in the regression models here, what we need to do is we need to formulate it such that they become we need to formulate it then by using the following one, the x prime x inverse x prime y. Okay, where we can be write down all the x matrix, the y matrix, and then the x prime x and x prime y. Okay, then we can be using the x prime x inverse x prime y. Then we can obtain what is the beta hat for this particular model. So similar to the following example here, if you want to do that, we also can be formulate it using the matrix forms. But one good thing is if this one is a 2 power k factorial design, our parameter estimates we can be get it from the effect itself. Okay, from the effects of the models. Therefore, I show you the effects here. Okay, so under the regression model here, let's say we want to consider, under the regression model, we consider, okay, the following regression model. Okay, we consider this is a model we have. Okay, or I use A to represent the factor A plus the beta 2 XB, okay, plus the error term. So we consider the following model. Okay, without the iteration first. Of course, we can be put in the iteration effect here. Okay, so if we consider the following model here, so the XA and the XB here. So we need to be careful about what is the XA here. So the XA here, I will call it as a quoted variable. Okay, where they quoted it means that they can be take the negative and the positive one. Okay, I try to do the coding. They can be have a negative, they can have a positive. Similarly, for the XB, we also can do the quoted variable where we have a negative one and the positive one. Okay, this one is what you can see from here. About the here is a negative one. About the low level is a negative. And the B, factor B is also negative. So I use a notation -1 and +1 to denote it as the quoted variable here. Okay, so you have because this one is do the coding of the variables. But if you observe it, this one is a 2 power k factorial design. Actually, the original value here, if you observe the table here, this one is your original value. The original value of the factor of here is a pound, is a U, and the second one is your the one is a low level is 1 pound and the 2 pound. But after you do the conversion, they become the -1 and the +1. Similarly, for the reaction concentration, you are doing the coding, they become the -1 and then the +1. But before that, the initial value, it should be called the 15% and the 25% of here. Okay. So we in the following example here, we have a we have a following section. It's called the I denoted it as a quoted variable here. Okay. So if we want to our regression model here will be based on the quoted variable, means that the XA and XB we're using the -1 and +1. But after we form the equation, we still can convert the XA and XB to the before I mean the original variables the values of this variable, what we call as a natural variable. Okay, so you can observe it. The factor A is the 15% and the 25%. The here is a 1 pound and the 2 pound. So how are we going to convert it? So to get the here, okay, so we can say that the relationship okay, we want to find the relationship of the what we call as this one is called the quoted variable where you have and the natural variable. Okay, how we want to find the relationship of here, we can be formulate is given by the following one. Okay, okay, so the relationship in between the natural variable these two with the quoted variables is given by the, okay, how we want to find the relationship of that is actually the XA is equal to the what we call the concentration plus the concentration at the low level plus the concentration at the high level, okay, divided by 2. You take the average value of these two concentration, and then after that, sorry, here is not the plus, here it should be the minus divided by the concentration of the high level minus the concentration of the low level over 2. Okay, so you can observe it this one. So what you can over 2 here. So we refer to the just now the concentration low. The concentration of the low, this one is the concentration low is 15%. This one is a 25%. So if you observe it, if the concentration of the low equal to 15%, the concentration of the high is equal to 25%, then you can see that the relationship of the natural variables, the original variables, with the quoted variable, how is it they look like? So we can have here, okay, we can have here what you have here is just the you have the XA, okay, XA will be equal to the concentration, okay, minus by this 2 is the plus over 2. It means that the 15 plus the 25 over 2 divided by the difference here is equal to the 25 minus 15 over 2. So therefore you get the XA will be equal to the concentration minus away the 15 here is 40 over 2, you get the 20, okay, divided by here is a difference is a 10 over 2, you get the 5. Okay, so your XA can be written as the following one. Okay. Sorry. Okay, so you have here the XA. So if you observe it, if the concentration is equal to 15, so you can observe that if the okay, if your concentration is equal to 15, if concentration is equal to 15, so you can observe that what is your XA? Your XA will equal to the 15 minus the 20 divided by 5. You get is a minus 5. Minus 5 divided by 5, you get minus 1. So if the concentration is equal to 25, so the XA will equal to the 25 minus the 20 divided by 5. So you get is 1. So therefore, why this one, the quoted variable, you have a value minus 1 and a plus 1. Okay, so this one is a reason how do you want to find out the relationship of the quoted and the natural variable first. Okay, you need to know this thing is because later on you from the equation here you can convert your equation in terms of the natural variable. Okay, so the same process will be applied for the XB. Okay, XB is referred to the B will here will refer to the what you have here. The B is a amount of the catalyst. Okay, so what I can do the same thing for the XB. The X for the B will be equal to the catalyst. Okay, minus away. If you still remember, this one is for the catalyst at the low level plus the catalyst at the high level over 2 divided by, you get the difference. So it's a catalyst at the high level minus the catalyst at the low level divided by 2. So therefore, the XB, you have the catalyst minus away because the low level of the catalyst is 1, the high level of catalyst is 2. So 1 plus 2, you have a 1 plus 2 divided by 2 divided by 2 minus 1 divided by 2. Okay, so and out you will get your answer for the here the relationship in between the quoted variable and the natural variable will be equal to the catalyst. Okay, minus away here is a 1.5 minus by 1.5 divided by here is equal to 0.5. Okay, so this one is how you want to find the relationship of these two first. Okay, so now we go back to the equation here. If you want to form the regression equation or the fitted regression equation, it's easy. We can get it out from the here. Okay, so I can say that the fitted equation, the fitted regression model is actually is equal to the fitted is a y hat will equal to the beta naught hat plus the beta 1 hat x for the A plus the beta 2 hat x for the B. So how to find the beta naught hat, beta 1 hat, and the beta 2 hat? Still this thing you can be using the following way to using the x prime x inverse x prime y, then you can get your beta hat where they consist of the beta naught, beta 1, and beta 2. But because of we are doing the coding of the to the one is a minus, one is a plus. So therefore, your fitted equation, actually this one is the beta hat will be beta naught will be just the mean of the data. Okay, the beta naught is just the mean of the data plus the beta 1 hat here. We can be using the just the effects of the factor A divided by 2. Okay, so this one is what you have here. Okay, so if under the 2 power of k factorial design, and then the full models here, the beta naught hat is actually the mean of the data. The beta 1 hat is actually, if you're about the XA, then it's the effect of the A divided by 2. For the beta hat 2 will be the effect divided by 2XA. So this one is you can be do it directly for the case of the 2 power of k factorial design. Okay, so therefore you no need to, not necessary, you need to formulate in the following way. Unless that one is not the 2 power k factorial design or they are incomplete model, then it's possible that you need to recalculate it again. Okay, so in the equation here, because just now I have shown it to you, what is the fitted the effects of the A is 8.33, the effect for the B is equal to -5. So therefore, we can be form the equation will directly, the fitted equation will equal to the mean. The mean means that the average value of the data. The average value of the data is from here. You have a data set. All the data are given here. 80, 100, 60, and the 90. You have all these values here. You total out, and then you take the average of all the 12 of them. Okay, so you will get your average value for the first one will be equal to the 27.5 plus, okay, the effect for the A here, the effect of A just now I have shown it to you is 8.33 divided by 2 XA. Okay, then plus the effect for the B here is equal to the -5 over 2 XB. So therefore, you get your equation will be equal to the plus the here will be the 8.33 divided by the 8.33 divided 2. So you get is a 4.165 XA plus here is minus 2.5 XB. So this one is your fitted equation. Okay, so you no need to use a regression here. Of course you can be use a regression, then you also can be get out the estimate of all these 3 values. Okay, but this one is in terms of the XA, in terms of the XB. So means that the XA can be the negative or the positive one. The XB also can have a negative one and the positive one. But we also can be change it. We also can be change it to the natural factors. Okay, means that instead of the natural here, we want to substitute the value as the, if you are talking about the catalyst, you want to substitute the value 1 and the 2, then we can be use the following one to replace it, then we can convert it back. Okay, so therefore our fitted equation under here, under the response equation, okay, or the response surface equation, we have a fitted equation will be equal to the 27.5 plus 4.165. The XA just now you have is a concentration minus the 20 divided by 5. Okay, then minus by 2.5. The XB is referred to the here. The XB will be referred to the catalyst minus a 1.5 divided by 0.5. Okay, so we have a catalyst minus by 1.5 divided by 0.5. Okay, so we can rewrite out the equation is become here Of course, this one multiply here become constant, so you will get is 18.33 plus 0.8333 concentration minus 5 times the catalyst. Okay, so your equation can be in terms of here, or you can be convert it back in terms of here. Okay, if your equation here, then you substitute the catalyst as a the concentration here you substitute as a 15 and the 25. For this one, the catalyst you substitute a 1 and the 2. For the XA here, because it's a quoted variable, then you substitute is -1 and +1. Okay, so this one is what you have under the how do you get out if you want to do the fitting of the linear models with the just the main factors. Of course, you can have another option if you want to find out your fitted equation. Then you can find out the beta hat will equal to the x prime x. Okay, you can be using this way where you can find out your fitted equation. Okay, means that you use this one, you get the fitted equation of the 27.5. Beta hat is 27.5, 4.165 to -2.5. Then after that, you convert it to the equation with the natural factor levels. Okay, so this one is an example. If I want to fit it for the first one, if I want to fit it for the regression, linear regression with just the mean effect. Okay. So if you observe it, this is a diagram. We fit for the linear model. This one is a diagram what you have. Okay. If you draw the response surface, this one is the equation here. The fitted equation will be given by the y hat. Just now you have a y hat will be in terms of the catalyst and the concentration about this equation. Okay. Then you can be draw in the three-dimensionally. The y, this one is the x, this one is catalyst, this one is concentration, will be the linear form. So if you draw the line, you cut it, then they become the control shot. Okay. So for each one of them, you just cut it here. So you will get the line here, you get the one of the line. You cut another one of the plane here, then you get another line. So of course you are not doing it manually here. You're using the computer base to do it. Then you will get all this line. So because this one is a straight line here, they will be related to the what is the equation you have, because your equation is linear. So therefore you will expect you will get your linear graph. So as you can observe it in the control plot here, the yield of the is 23, 25, 27, 29, and so on. Means that you are using the high level of the reaction concentration for the high value of here, and then at the same time you lower your catalyst amount, then they will towards the high. The yield of the process or the chemical process will be higher. Okay, so this one is what you can see from the control plot. Okay, so this one is what we can go based on this diagram here. Okay, the diagram here is show you that the three-dimensional response surface plot on the from this model, and then the figure 8.3 is the control plot. So because of this one is a first order, you only concentrate on the main effects. Okay, your model consists of the A and consists of the B. So you only concentrate on the main effect. Therefore, the fitted response is just a plane. Okay, so for examining the control plot, we see that in the yields increases as the reactant concentration increases and the catalyst amount decrease. So as I mentioned to you, you can see this one is your Y, this one is your response of the Y. So you want to get the higher Y, then you need to go to this direction, and then here you need to have a smaller value. So this one is what they mentioned of here. So based on this thing, because we also interested about looking for the optimal solution, so we use the fitted surface such as this to find the direction of the potential improvement for the process. So a formal way to do it is called method of the signal action. So this one I will discuss with you later on. Okay, if today can finish, then I will discuss with you about all these things. Okay, so we using the technique is called the method of the signal action or method of the signal decision to locate for the optimal solution. Either the solution is maximum or they go for the minimum. Okay, so this one, before you can draw this thing, of course, you need the equation. You need the equation out. So before you get this equation, you also need to check whether the factor itself is contribute to the y or not. If the factor is may not be the significant, then we may not be include it in the model. Okay? So this one is the first part of the response surface of here. Okay. Then after that, because this one is a linear line, of course, before I go to the next page, we also can have it. If we want to fit the regression, if we want to fit a regression model with interaction, okay, we want to fit the regression model with the integration, then our equation will become the y will equal to the beta naught plus the beta 1 xa plus the beta 2 xb plus the beta 3 xa xb plus the error. This one is a model we have. Okay, the model we have here. So again, even though here have an iteration here, we still can be using the effects to replace it. So the fitted equation is just a beta naught hat plus a beta 1. Okay, so we have here. So this one will be equal to the mean. The fitted will be equal to mean plus the effect of the A over 2 XA plus the so this one is still replace the same thing, where the first one will be the mean, this one will effect over 2, effect over 2, effect over 2. So how to calculate the effect in the 2 power k factorial design you have studied before. Okay, so under the in this chapter we will concentrate on the 2 power k factorial design. Therefore, our fitted equation here we don't necessarily need to use the what you have used it here. Okay, to calculate the beta hat. Okay, so this one is the first example I go through with you. Okay, so in the previous study, this one is the example 6.1. I also have discussed with you all in the chapter number 6, where we have here we have an equation is given by here. This is the data set what we have before, and then here is all the treatment combination. And then we run it out the experiment to identify which one is the important factor. Okay, so how do you want to know which one is the important factor? Then you use the analysis of variance to check which one is the important factor, and then whether they have a significant difference or no. Okay, so you run the ANOVA, okay, or you calculate the effect first, because this effect later on we will use it for formulate the regression equation. So this is the effects. If you calculate out, then you can calculate effects, and then you also can calculate the sum of square. This one we have discussed previously. And then from here, the percentage of the contribution of sum of square, we try to identify which one is the important factors. So from here, you observe that this one and this one, the value is quite high. So we will suspect that these two will be the main contributor for the equation here. Okay. So from the equation of the here and then of course this one is all nearly zero. This one XA maybe also is possible here. Okay, so we can be identified that these three is considered as important factors here. Okay, then of course we run the analysis of variance. We run the analysis of variance here, then to confirm that. So if we set the alpha is just the 5%, okay, we set the alpha 5%, then we compare with the p-value here. Obviously, this one will less than the alpha. Then this one also less than alpha. This one is a less than alpha. So means that the factor A, the factor C, and the factor AC are the important factors here. Okay, what you have studied in your chapter 6 before. Okay, so now based on these factors here, we just proceed with formulate the regression model. So since the factor A, factor B, factors A, factor C, factor AC are important, so we can form the regression model. So the fitted regression model, okay, so the regression model for predicting for the predicting each rate will be equal to the y hat is equal to beta naught hat plus the beta 1 hat x for the factor A, because factor A will be important, so we can put in the model here. Then after that we have C and the AC, so we have this one plus the beta 2 hat xc plus the beta 3 hat xa xc. So this one is your fitted equation. So based on the fitted equation here, then we can be check out what is the effect of the factor A. So the factor A will be effect will here, the factor B is here, and the factor AC will be this one. So therefore we can be put in our equation here. Okay, of course the first one will be the mean. So the mean is the average value for all the observation. So you get is a 776.0625. Okay, plus the beta 1 effect of the beta 1 will be negative 101.625 over 2 for the XA plus the 306.125 over 2 XC plus the third one will be the negative 153 XA XC. So this one is your equation. Okay, so we can have a fitted equation will be given by the following one. Okay, so of course from the XA XC here, because if you observe it, the XA and the XC actually is here I do not mention it. Of course the XA and XC, the XA and the XC, they can be only take the value minus. They can take the value -1 and the +1. Similarly, for the SC, also can take the -1 and +1, so that we can use the effects of the here. Okay, the effect for the factor A here divided by 2, the effect for the factor C divided by 2, the effect for the iteration divided by 2. So of course you get your XA XC, you can be used it from the coded variable, you convert to the natural variable. Okay, so this one is what you have under the second example here. Okay, in the regression. So the following one, because this one you have a linear model plus an iteration effect there, so they are no longer the linear line anymore. If you observe previously, what our model we have is only the linear model. We have only the linear model here. So if you have a linear model here, then therefore you your control plot and your the response surface here will be the linear. But in the following example, we are no longer the linear because we have a iteration terms there. So therefore, the equation will be look like the following one. You have a certain curvature parts. Okay, it's no longer the straight line here, but of course they will convert it to the power level. They convert it to the let me see. If we have the original, the default, yes. Okay, the default I have given you here. What is the factor A? Is a 0.8 and the 1.2 for the factor A. Factor B will be the 1.2, 125 and a 200. The factor C will be 275 and 325. Okay, so of course we can do the conversion if we wish to do that. So we can have a XA will be equal to the quoted variable will be the A is referred to the gaps. So we have a gaps here. Okay, the gaps here plus minus away. Just now, how do you do it? You just take the average value of these two. If you can recall back what you have before. Okay, the first one is you use the catalyst minus the average value divided by the difference over 2 also. Okay, so therefore in the following this example for the XA, it's just a gap here, and then you use the 0.8 also can, plus the 1.2 over 2 divided by the difference. The difference will be 1.2 minus 0.8 divided by 2. So therefore you get the gaps minus away. Here is a 2 divided by, you have 2 divided by 1, the 2 divided 2, you get 1 divided by, here is a 1.2 minus 0.8 divided by 2 here. So it's 0.2. Okay, so this one for the XA. For the XC, you have the XC is referred to the power minus away. The first one will be the power is a 275 and 275 plus a 325 over 2 divided by 325 minus a 275. Okay, and then this one is here over. Okay, 325 minus 275 divided 2, you get 25. Okay, to be confirmed that whether your answer is correct or wrong, you just substitute the gaps here. You just substitute the original gaps is a 0.8 here. So you use a 0.8 minus by 1 divided by 0.2, you get the answer is a minus 1. You substitute the gaps with the height level 1.2, you get the answer is 1. So means that you're doing the conversion are correct. Okay, for both of them. So this one is an equation, the fitted equation here. If you want to get the following contour in terms of the power and the gaps here, of course, you need to substitute the XA gaps minus 1 over 0.2, and then the power here is a power minus the 300 over 25 in the following equation, XA and the XC here. Then you rewrite the equation, then you can get out the equation, it follow the following contour plot. Okay, so from the following contour plots, what we can observe from the following contour plot here. So if you observe the following contour plots here, of course this one we know that there's just a slanting here. But if you based on the value means that you cut the line by line here, then you can see that if you going to for the minimum, or we going for the age rate, if we are looking for the minimum, then we know that you decrease the gaps here, you reduce the gaps here, and then for the low power level, then you get the smaller value. If you're looking for the maximum, then you know that they happen at here. Of course, this one is just depends on how do you cut. So this value is just particular cutting. But this value may not be the smallest, may not be the optimal or the minimum. This value also may not be the maximum, because if you cut some more, then you get the line is like this one. Okay, the bottom you still have a line here. Okay, so this one is just show you from the computer software, they just to show you the cutting. You can see the trend of the hair. The trend is decreasing in the following direction. You decreasing in the following direction, it means that you can see this line is just a slanting. So maybe they are towards for this one, the less than the 1. The gaps is less than 1, you get the minimum. And then at the same time, your power level, you decrease the power level. So they were towards the direction of the here. Okay, so this one is what you have before. I have mentioned it here. This one. You have a following control plot, then you slowly move to the direction, then you get the optimal solution. Okay. Okay, so this one is an equation here. Okay, the equation of here, and then you can convert the XA, XB in terms of the power here, then you get the fitted equation. Okay. So this one is for the second example, the following example. Okay, then after that we have a third example here. This example also is in the chapter number 6, or you can refer to the chapter number 6 lecture note. You also have a similar example. Now I just add on with the response surface for the 2 power k factorial design. Then we just form the regression equation. Okay. So far, our regression equation is just a first order, and then the first order plus the iteration. Okay, because if you study the 4 factors, the factor A, factor B, factor C, factor D, then you can get all the iteration effect. Okay, so all the iteration, their effects, you also can calculate from the contrast. Okay, so in the following example, we study is 4 factors here. Then based on this 4 factor factorial design, the 2 power of k factorial design, then we can get the following effects here. So the effects is just calculate the using the contrast, you calculate all the effects here. Okay, so from the effects here, you can calculate the sum of square, because there is a relationship in between the effect and the sum of square. So from here also, we want to know that which one is really contribute more for the sum of square. So if you observe the value here, majority of them is nearly 1 or the 0. Only this one is 32. The contribution of the sum of square is 32. The contribution of the D is 14. And then this one is 6. And then this one is AC is 22. The AD is 19. So these 5, the first one, these 2, and these 2, since that they are the main contributor. Okay, but anyway, we still cannot confirm it. So therefore, we run the analysis of variance. Okay, but because this one is only they deal with only the single replicate here, only the single replicate here. Okay, they only real for the single replicate. So if you still remember, when you want to run for the single replicate, you can be identified the important factor, but you cannot carry on the ANOVA. Okay, you can be assumed that certain higher order iteration is not significant. One way you can do that. The second way is you plot the normal probability plot. Then from the normal probability plot, you identify the important factors. Okay. So in the following one, this one, okay, we will using here the result from the examples in the table 6.13. So we just concentrate on this particular factor of here. Okay, we remain these of the factors. After that, the rest of them, they will go for the error. So as I mentioned just now, you can have another option is draw the normal probability plot for the effects and then identify which one is the important factor. Okay, or you assume that certain high order iteration is not significant. So that one is quite subjective. You have a different type of the answer. So in the example here, they will concentrate on these are the tier. They remain that those of the iteration of the factors here. Why they remain this one in the factor here? They don't want to pull it to the error. One possible reason is because they think that if the A, C, D are important, so therefore they put the CD iteration also here, and then they want to check whether this one is also they are important. Then because the ACD are important, therefore they put it the ACD here. Okay, so this one may not be the final answer or may not be the only answer. It depends on what is the way you want to identify the important factor. So based on the ANOVA, what they're given here, we know that these are the important factor here. These are the 5 are the important because the p-value will be small if we compare with the alpha 5%. So all these things is a significant. So means that we can formulate our regression model. Okay, so our regression model will consist of the beta hat will be equal to the beta naught hat plus a beta 1 hat for the XA plus the beta 2 Okay, so these are the 5 factors here. All these one, their coefficient you can obtain from their effects. Okay, so therefore we will get the first one, the average value. The first one will be average value is a 70.06 plus the first one will be the effects here. The effects, if we recall back the previous example here, the effect for the A is equal to 21. After that, the C is 9, 14, and then negative 18 and the 16 here. So therefore, in our here, we have a 21.625. Okay. Okay, so we have a following equation here. Okay, so from the equation here, if you want to know that what is your results? Okay, what is your results? If you're running out the all of them at the low level or some of them XA, XC, and the XD at the different levels. So for example, if the XA will equal to -1, the XB will equal, sorry, not the XB, the XC is -1. If this two is a -1, and then after that you also have the D is a XD will equal to -1. If all of them at a low level, then we can calculate out the Y hat here. Okay, the 70.06 plus the here will be the okay. If this one is a set of the data, okay, if all we want to know that what is the estimated value of the fitted value, then we substitute out all the low level, then we get the fitted value is equal to 46.22. Okay, so this one is what you have for the response surface here. Then this one again, this one is the surface, the response surface is the XA, XBC, and the XD, and then together with the those of their iteration. So we will expect our control plot is no longer the straight line, they have a certain curvature pattern. Okay, so this one is what you have the first plot here. Okay, under the first plot here, the control plot, because when you want to draw the control plot, you only can have the two axes, the x and the only the two axes here. So these are the plot here. Okay, we will fix it for the x4 is equal to 1. Okay, so if we fix it, the x4 is equal to 1, then our equation will be reduce it in the other form. Okay, so if we observe that this is the equation what we have here just now. Okay, this is a fitted equation here. If our x4 is actually they refer to the, because the diagram here is using the x4, I'm using the not using the x4, is actually the xd is equal to 1. So this one x1 is actually the xa is equal to 1. So if the xd is equal to 1, how we want to get the equation? From the plot number A here, the fitted equation for the xd will equal to 1. Okay, so what is your fitted equation? Will be 70.06 plus the xd will equal to 1. So you have the first one is 21.625 over 2. Okay, for the xd equal 1, so we replace the xd is equal to 1. So from here, your equation is still have a mean plus the xa, okay, then plus the xc in terms of xc, and then you also have another one is a xa, xc. So you still have a iteration effect when you fix the xd equal to 1. So therefore, we will expect that they consist of a certain curvature pattern. Okay, so if for this one, the filtration rate, you are looking for the minimum or you can looking for the maximum, then you will know that in the following direction, where we get the minimum, in the following direction, you will get the maximum. Okay, so for the second plot of the here, for the second plot of the B here, for the XA is equal to 1. We fix it as a XA equal to 1 first. Then therefore, we get the fitted equation. You just replace the XA will be equal to 1 here. So the XA equal to 1, the XA equal to 1 here. So end out, you will get your equation is only consists of the do not have a XA anymore, because you only fix it for the XA is equal the XA is equal to 1 the XA is equal to 1. So you substitute XA equal to 1, all these things is become the constant, so you will merge together with here. So you only have the XC plus this one is a XD, you have a XD here, and then plus the this thing is because XA is a 1, so this one is become the XC. So therefore, it merge with the XC. Here is XA and XD. So the XA is a 1, so you only have XD. So therefore, you only consist of the 3 of them. Okay, if you fix the XA equal to 1, you only have a constant plus the XA plus the XD. So therefore, you can see that it's a linear line. You have a XC and the XC and the XD is just a linear line, because your equation will be the linear line. Okay, so this one is what you can be use your effects, and then you calculate out the from the effects there, you can be form the equation. Okay, so where your equation consists of the main factors and the iteration factor. Okay. So we also can have the, just now at the beginning of the section, I also say that we also can involve the quadratic effect there. Okay, so that one is here in the beginning of section here. I also mentioned that we can have a second order. Instead of putting the iteration effect and the mean effect, we also can put the quadratic effect here. But is it the quadratic is important or not? The first thing is we need to check whether this quadratic effect should be included in the model or not. The first thing. The second thing is because we do not have the calculation of the effects for the quadratic effects. Therefore, we cannot be calculate the beta anymore. We need to use the just now what you have the in the regression model. If you want to do it, then we need to use the following regression and then calculate the beta hat here. Okay. So in the following section, I would let you know whether we want to include the quadratic effect in the model or not. Okay. Okay, so this one is what we have. The following section is called the include the quadratic effect in the model. So how are we going to include the quadratic effect? Then we need to have an extra point to do the checking. Okay, so how I say the extra point for the do the checking is this one is called the response surface. Okay, for the response surface of them. Okay, so we adding the center point here. So adding the center point is refer to the center point here. We refer later on. I will show you in the following diagram. Okay, addition of the center point to the 2 power of k design. So first thing, I repeat the same thing. In the linear model or the first order model, this one is only concentrate on the mean effect. If the iteration plus the mean effects or the first order one, then you have the certain curvature. But sometimes you also need to go up until the second order where you include the quadratic term here. So first thing we need to check whether this quadratic effect is important or no to be included in the model. So how are we going to check it? Then we were using the following test to be test whether the quadratic effect is important or no. But before we do the testing of the quadratic effect, we need to have extra runs. Okay. So we need to have an additional of the center point. So because we are doing the coding of the xi is the coded variable. Okay, if you still remember the xi here, I do the coding of the variable where they have a -1 and the +1. So the center point here, we use a notation as a 0. Okay, we use a notation as a 0 to represent the center point. Okay, so therefore, in the previous example, in the regression, you can see you have a 0 here. This one is actually the center point. You have a low level, you have a high level. Then you have a 0 here. This 0 is referred to the center point. Okay. So to run for the second order, then we need the center point to do the checking of the x square, whether this x square will be important or not. Okay. So the following diagram will tell you what is called the center point here. So in this diagram here, I just show you this one is an example of the 2 power of 2 design with one observation here. Okay, with only the single observation. So this one is a low level for both. This one is a high level for the A. This one is a high level for the B. This one is a high level for both of them. Is we give the notation as a AB here. So these are the 4 points of here. So we use a name is called the factorial runs. So the NF is referred to the factorial runs. So in this case, the factorial runs, you have a 4 factorial runs here. Okay. And then the center point, or because here is -1 + 1, here -1 + 1. So therefore, the center point here will be the 0 and the 0. For the x1 is 0, the x2 also 0. So therefore, here I will call the NC is referred to the number of the center point you run, or the NC observation at the center point. So because you only study the two factor, therefore it's 0, 0 here. Okay. And then the YC, the Y bar here is I think I need to enlarge it. The Y bar here, the C here, it means that the average value of the NC runs at the center point. Means that the average value for the center point. Okay, the NF here is a number of the factorial design. So in this case, because we deal with the only single replicate, so therefore the NF here, you have a 4 factorial point here. So the NF will be equal to the 4 here in this particular case. The Y bar F here is means that the average value for 4 runs at the 4 factorial point is just the average value. Okay, so we want to compare the way of the compare the quadratic is like this one. We have these 4 points, and then we also run the center point. So from the center point, we get the mean for the C. From the 4 factorial point, we get the mean. We get the mean for the factorial point. Okay, of course, the mean of the factorial point should be inside. Okay. Okay, maybe our mean for the factorial point will be here. So we want to base on this mean and this mean to do the comparison. Okay. So based on these two means here I have mentioned, if the difference between the mean of the factorial point, the mean for the factorial point and the mean of the center point is small, then the center point is lies near to the plane pass through the factorial point, and this is no quadratic curvature is needed. Otherwise, the quadratic curvature will be present. So if the quadratic curvature is present, therefore you may need to include the quadratic terms in your model. Okay, so the reason is we are testing about the here. We want to get the mean, then we do the comparison here. Okay, so this one is what is the plane here. The mean of the factorial will be here. The mean for the center point will be here. Then they do the comparison. Whether how far is it these two, the mean for the center point and the mean for the factorial point. Okay, so this one is here how we want to test it for the quadratic effect. So how are we going to test it? Here I show you the formula how to test it. Okay, so the sum of square for the due to the pure quadratic curvature is given by the here. The sum of square for the quadratic here will be equal to NF plus NC, and then you get the difference of the here the mean for the factorial point and the center point. You square out divided by NF plus the NC. Okay, then our hypothesis is actually we want to test whether the quadratic effect is necessary or not. So we are not testing for the individual, we are testing in general for all. So therefore, they just testing for the overall sum of them. The JJ is stand for if you study the K factor, so all of them, whether the quadratic effect must be in. If they equal to 0, means that the quadratic effect is not necessary. If they not equal to 0, means that the quadratic effect should be included in the model. So therefore, your regression model consists of the quadratic effects. Okay, so how are we going to test? Actually, we are still using the F test, the F statistic. Okay, so this one is the point you have. The F statistic will equal to the mean square for the pure quadratic divided by the mean square for the error. But you bear in mind that in this case, we do not have the MSE because you only study is over here, you only have a single observation. Therefore, you cannot estimate your mean square error. So how are we going to estimate the mean square error? Before that, you just throw away those are the not important factor to the mean square error. But now you do not know whether which is a factor, like this example 2 power 2. If you want to test the F ANOVA, of course, the iteration of the X1 and X2, you throw it as a MSE. Then you can be test the significance of the factor A and the factor X1 and the factor X2. But over here, because now we run the center point, we run the extra thing for the center point. Therefore, now we have an extra information for us to estimate the MSE. So how we want to get the MSE here? Okay, I will show it to you. Okay, so if the factorial point is an unregularate, we may use an NC center point to construct an estimate of the error with n-1 degree of freedom. So how we want to do that is actually, if you want to estimate MSE, because you have run the NC center point. Okay, you have run the NC center point here. Okay, so to estimate the MSE, okay, to estimate the MSE, we can be use the MSE is actually is equal to the sum or square for the E divided by NC minus 1. It's a sum or square divided by the degree of freedom is NC minus 1. So this one I call it as a pure error. Okay, I call the name as a pure error. So how we want to calculate out? We can be calculate out based on the center point here. So where we have just a sum of the point here, the center point minus the mean of the center point. You square it out divided by the NC minus 1. So this one, the sum it out is actually sum out for the center point. Okay, the sum out only for the center point. You square out divided by n minus 1. This one is quite similar to the formula for the variance. Okay, but you only use your center point here to calculate your MSE. Okay, so this one is what you have here. Okay, so how the formula you can obtain from the above here, from the above one. Okay, how you want to show the formula here, I can show it to you. So suppose we want to test, if you recall back what you have here, suppose I want to test that if the difference is a small or large here, the difference of the YF minus a YC, is it small or large? Then we can be testing the following one. Okay, instead of writing in the following one, we also can be write in the following one, where we have a H naught, the mean for the F will equal to the mean for the C. Is it the mean of the factorial point will be equal to the mean for the center point, or our hypothesis alternative will the mean for the factorial will not equal to mean for the center point? So this one is what we're going to test. So if you're testing for the two means, you learn the statistic. Testing for the two means will be equal to the jack here. Okay, if we provided the variance is known, then we have a mean from the factorial minus a mean for the C. Okay, we will have the following one. This one is what you have here. Okay, so we need to do some assumption that if the variance is here, if the equal variance, assume that sigma square will equal to sigma for the F square equal to sigma for the C square. If both of them have a common variance, therefore we have a jack will equal to the okay, you have a following the jack here. Okay, so you can be square it out. Okay, because this one is follow the normal with the 0 and 1. It's a standard normal. You standardize it, it's follow the standard normal distribution. So if the standard normal distribution, you square it out, you square the jack here, so you will get the following one. You will get the following one is actually your jack here, the jack square, they will follow the chi-square distribution with the degree of freedom is equal to 1. You square out the whole term, then you will get your jack is follow the standard normal distribution. Follow the chi-square with the degree of freedom 1. Okay, I think you learn the statistic, you will know from the standard normal, you square out, they follow the chi-square with here. Okay, this one is the first one. Also, just now the MSE, what you have here, the NC minus by 1 multiplied by the MSE divided by the sigma square. This one will follow the, okay, before that, I just show it to you here. This one is a MSE, so this one will equal to the NC minus by 1. The MSE is actually the SSE divided by NC minus 1 over sigma square. So it's actually the SSE over sigma square. Okay, so this one, the SSE is equal to the sum of the yi minus the mean for the center point square, center point here, okay, divided by sigma square. If we write it out here, it's actually this thing. Okay, this one is actually follow the chi-square with the degree of freedom is equal to NC minus by 1. Okay, so this one is another fact. The first one, the fact here. The second one will be the second fact here. Okay. So from these two facts, then we can be simplify it out to the following formula here. Okay. So you have a T distribution. The third one, the T1 will equal to the jack over. Okay, is equal to the jack divided by the okay, you have a jack. Okay, you have a jack here. Okay, on. Okay, so I repeat here. You have a two fact here. One is given by this one. The jack square will be given here. The second one will be given by the chi-square. This one is a chi-square. This one is chi-square. Okay. The third one, what you need to know is actually is a T distribution will equal to the jack divided by square root of the chi-square distribution divided by their degree of freedom. Okay. This one is a T distribution here. Okay. The T distribution of here. So if we use the jack here and then divided by this particular function here, okay, then later on, or we divided by these parts, then you can see what you have. So the jack will be equal to this one. Okay, it's a mean for the C, mean for the factorial, mean for the C minus the. Okay, so of course this one I try to make the denominator the same. So we have we can be factor out the sigma out here. So therefore we will get the sigma here. Then we square root of the n for the C and the n for the F. Okay, you will have this thing. Then the whole thing will divided by. Okay, maybe I will remove the equal sign here. I'll put this thing will equal here. This whole thing will equal. This one is a chi-square here. You take the square root of this whole thing. Square root of the NC minus 1 MSE divided by here the sigma square. The sigma square here is a chi-square over their degree of freedom. The degree of freedom under this thing is equal to NC minus 1. NC minus 1. Okay, so from here, we can be further simplify it out. Over this sigma and this sigma, in fact, you can cancel off it. Okay, the sigma you can cancel off it. Then the NC, the NC minus 1 and the NC minus 1, you can cancel off it. Okay, So you will left only the MSE, the square root of the MSE. Then you have a square root of the whole thing is a NC plus a NF divided by NC and F. Okay. So under the H naught, the mean F minus the mean C will equal to 0. Okay, because under the H naught is a mean C minus mean F, or you have a mean F minus a mean C will equal to 0. Okay, under the H naught you have this thing. So therefore, your T will be equal to the YF minus a YC divided by square root of the MSE. Take the square root of the NC plus the NF over NC and F. Okay, you will get the following one. Okay. So yeah, so you have this thing. The reason I do this thing is actually finally I want to show you about this one is a formula you have. Okay, it's the formula of this part is almost already come out. You can see you have NF and so on. Okay, I show you this thing is here. So we have another one more step so that we can have a following one. So now it's already 7:34. I think we stop for the while. Then we will continue later. Okay,